So good morning. I'm very grateful to the organizers for organizing this event and for inviting me and giving me the opportunity to speak. And it's great to see you all here. So in the preparation of my talk, I was guided by the applied topology. And I thought that I should show you a number of results, some old, some new, some in progress, that for me are really the main motivation of why we do what we do. So topology, and in particular topological data analysis, is great if it can actually tell us something about some important problems that people want to solve. Okay, that's somehow the whole point. Okay, I know that there are many fascinating theoretical problems and things to solve, but somehow let's see what it can do for the sciences. So, apart from mathematics, my main passion is physics. It's the amazement that we can actually describe the material reality of the world I never got over it. So it's worth pondering that somehow you can take a fragment of the universe and understand it completely. And topology deals with that very beautifully, because here is a very rough diagram of how all of the science works. Everything that we see around us has some kind of structure, which is known or unknown to us. It may be exact, it may be hidden in some complications. But physics, or what we understand of physics, is essentially a manifestation of some structure. Okay, things are organized a certain way, and they do a certain thing. That's physics. Okay, but topology, as you well know, it also reacts with structure. If you have a particular kind of structure, you have a particular kind of topology. In what I'm going to talk about, I will hope to show you that there is actually a link either through this structure or directly between topology and physics. But as you know only too well, reality is messy. That somehow is a defining feature. It's just messy. In particular, it's all very well to talk about structure, but it's always interrupted by some sort of disorder, and disorder is ubiquitous, is ever present. And if you want to get rid of it, well, it's possible up to a point, and it will cost you a lot of money. It will be very, very difficult. And at certain scales, it will be just essentially impossible. So the question is, if you allow the disorder is a fact of life, and you know that physics, well, it just adapts and it still works, is there anything meaningful that we can say about systems that are not that are ordered precisely? And can we still say something about physics? Okay, so just so that it doesn't sound so mysterious. In real life, we can cope with disorder. In fact, disordered materials, for instance, can perform fantastically useful functions. I know there are runners in the audience. Are there cyclists in the audience? Yeah, so you know that you want to be visible when you go out for a run or when you cycle, right? And there are numerous high-tech materials that reflect light tremendously well. There are those jackets that just seem to have their own internal light source. They are so bright. Well, in order for them to do that, you don't need to put anything sophisticated on that. It's just a bunch of glass balls, essentially. Well, it's more complicated than that. Nobody wants shards of glass on their jacket. But that's essentially, you can do it, you can paint a piece of fabric with some sort of solution of reflective particles, and that's it. There's nothing more that you need to do. It's completely chaotic, it's very disordered, and it shines like crazy in direct light, right? So that's an example of something which you never need to be ordered and does something very, very useful. I will give you examples of soft matter systems because they are tremendously complicated. They are everywhere. We are examples of soft matter systems as carbon-based life forms. You may or may not know that you're a soft matter system. We haven't. Yeah, it would be cool to meet a life form which is, I don't know, silicon-based or I don't know, a metal, something like a Terminator 2 kind of thing. But the variety is great. It starts with polymers, which are as ordered as you want. All the drinks bottles that you use will be made of polymers. Gels that you meet daily, they soft matter systems, all kinds of granular materials. Liquid crystals will form a major part of my talk, and then biological tissues of various forms. So, as you can see, biological tissues are examples of systems which are not ordered in any particular way, right? If you look at a picture of something like this, at best there is some partial structure, but a lot of this is just, it's very difficult to describe what it is. And yet, it organizes itself functionally. It knows exactly what it wants to do, right? So the fact that it doesn't look ordered doesn't mean that its function is disordered. It does something really, really wonderful. Okay. All right, so let's talk about what the physicists are interested in. They would like to achieve something called a self-assembly. They have all kinds of component materials, nanoparticles of various complexity, things based on carbon. Carbon organizes itself in weird ways, so nanotubes, nanoarrays, and so on. Graphene is partially ordered, but can give you platelets like this, nanoplates that on the one hand are fragments of organization, on the other hand they are completely chaotic, and so on. So you would like to achieve in physics what nature does without effort, has been doing for millions of years, right? So things just grow. Okay, we've all began from one cell, and that one cell divided itself so many times that it created many cells, and those cells just figured out what they need to do. And, you know, I have hands, I have eyes, I have ears. It's amazing, but it's sort of that's the kind of self-assembly that we are still nowhere near being able to replicate. Pretty much all systems that do something interesting will have phase transitions. They will go from one way of being organized to another. And there are beautiful examples within the world of liquid crystals where structure may emerge or disappear depending on how you cool things and how you heat them up and so on. And then structure may emerge, function can emerge without structure actually being there. So something like the defensive behavior of a school of fish, they don't interact in any way. They're not connected to each other, but they can organize themselves into a big cloud to confuse a large predator. And they will act collectively without actually being a single organism. And this collective behavior is fascinating. So let me begin by talking about time evolution in liquid crystals. So let me give you just a thumbnail sketch of what liquid crystals are. So these are substances that have a modicum of organization that sits between crystal-like, very precise structure and liquid, which is essentially disorganized. And the word I would like you to remember is isotropic, which is messy, chaotic, and nematic, which is well organized. Liquid crystals typically have those elongated shape, and they are like little magnets, so they will react with an electric field. You can organize them.
Are these molecules?
Sorry?
Are these
molecules?
Molecules.
These are molecules. Yeah, right. So these are individual molecules of liquid crystals. They are like, I would like to call them cigar shaped. I have no idea what cigars look like these days. So here is an experiment that our physicist friends from Warsaw performed. So you mix liquid crystals with gold nanoparticles, and you do that because those gold nanoparticles, they act as centers around which structure begins to grow. That's frequently happens in physical systems. That if you have some impurities in something, then this typically begins some process of organization. And you stick this liquid crystal with gold nanoparticles. Nano means that they are of nano size, 10 to the minus 9 meter. That's what nano means. And you put it in a really thin tube, put it between two polarizers, and I'll explain in a second why you do this, and you shine light and look at it from one end, or you shine light from one end and look at it from the other. And the point is that liquid crystals interact with electromagnetic waves, and in particular they can twist polarization of light. So if you have two polarizers at right angles, there is no light passing through. So if you see anything at all, it means that that the liquid crystal itself has shifted, has changed the polarization enough so the light is allowed through. And two ways you can see that the two phases between in the isotropic phase and the disordered phase, it will not do that. So there is no light going through. It will be black. And in the nematic phase, light will go through. So the liquid crystal itself has changed polarization. And after that, the result, and that's really something quite amazing. How do I make it play? Okay, so play. This is the result. Okay, so I gave you time to absorb the fact that to a non-specialist, it's very difficult to see if anything actually happens there, right? And if you see, yes, something is happening, why would I be excited about this? But this is science, right? This is when you're an expert in liquid crystals, you say, this is cool. This is, I'm cooling or heating something, and it's clear. I can see by this little video that my liquid crystal goes from one phase to another. And yeah, the result was published in ACS Nano, a leading journal, but can you actually quantify this? Can you actually make it more visually appealing? All right, so this is where precision homology comes in. So essentially what we take is, what we did is we took this video as a sequence of frames. Okay, so a video is a sequence of still frames. We calculated persistence for every frame in the term. And out of that, we built a video of persistent homology diagrams. Okay, so on the left is the video of the liquid crystal, on the right is the corresponding video of persistent homology diagrams. Okay, so something bubbles, classes appear, they disappear, and there is something should happen where this behavior is a little more Good. Is this is it the same? Okay, so let's right. So here's a different system of a similar kind, and we did exactly the same. So I'm showing it to you because although we still don't know what's going on, at least even at this level, I hope you will see that the behavior of this video of persistence diagrams, I bet you were watching persistence diagrams, not the capillary. The behavior of persistence diagrams actually is different in each case. So there is hope, okay? And by the way, the idea of doing this I don't think it's particularly new. I think Miro Kramer was making videos of persistence diagrams for quite some time. However, what is different here is that this describes a particular physical system. Okay. Good. So what we did is two things. From those time-dependent observations, we created the sequence of time-dependent topological descriptors, and then the norm of persistence diagram gives us a numerical characteristic, which is useful, and I'll show you in a second why. And there is another way, the fact that we are using persistence diagrams actually allows us to visualize this in a different way. And it works like this. So different levels of organization of that sample. So this is the ordered, this is the disordered phase, correspond to persistence diagrams. They look very, very different. And you can actually, because we know when this picture was taken, you can go back and check. And our physicist friends were very excited about that. So to start with, we did something quite simple-minded and naive. We just took the L1 norm of every diagram, so the total lifespan, if you like. And so that gives you a number for each frame. And we plotted that as a function of time. And you can see that it's constant, or more or less constant, for bits of time, and then jumps. Okay? But being the advantage of working with experts on this and knowing when exactly this was happening is that we could ask them to check, and they confirmed that what this is doing is what they were seeing themselves. These are the phase transitions within the system. But the advantage of doing it this way, and you see this is a wonderful example of the application of persistent homology. Now this is very precise. Before you had to just look at it and say, okay, it looks like this phase transition has started. But now you can know, you will know exactly when this happens. Okay, so and three phases: the nematic phase, which is one phase. There is also a period of time when the two phases coexist, and then there is the isotropic phase. And there is a clear distinction between levels of organization in each of the phases. So that was a good win. However, there is more. As you well know, it's possible to calculate distances between persistence diagrams. And so this experiment had two phases, the cooling phase and the heating phase. I'm afraid I've forgotten which is which, but one is cooling and the other is heating. And so when you take persistence diagrams with individual video frames of that video and calculate distances, right? So you get a metric space of video frames. And just even without any deep analysis, it's obvious from these heat maps that the structure of the metric space given by one part of this process is completely different to the other. Okay, they do not look the same. So you see, this was intriguing because the system, when you heat it up and then cool it down back to the initial position, it will go back to the initial state. All right, so it was easy to imagine that one part of this process is the inverse of the other. However, if you just compute this, it's very clearly from these heat maps of distance spaces and the embeddings using some multi-scale, multi-dimensional scaling, that in fact the process from heating to cooling and then from cooling to heating are not inverses of each other, even if they end up in the same position. And our physicist friends did not know that. It was kind of easy to assume that as you oscillate between these two stages, your system goes through the same setup. It doesn't. And this was persistent homology that did that. So I think it's interesting. And there are numerous beautiful examples that get more and more complicated. So you'll have cellular networks like this that your system begins bubbling up from small disorganized bubbles that hook up in these long strands, which begin to determine the overall, if you like, structure of your system. This will be the basics for any structure which is built later. Now, if you try to calculate persistent homology of that, you run immediately into difficulties with image processing. Okay, as I said, reality is messy. For whatever reason, you always get those dots, and you're not interested in those dots. You are interested in those lines, but the lines, as you can see, are not as contrasty as the dots. So if you try to clean the image, you can either get the dots or the lines. You can't get both. So after much deliberation, and I'll come back to this point later, in how to actually process these images. So that's before you even start talking about persistence, there is quite a lot to do there. But then, okay, if you overcome those difficulties, persistence works. It will tell you the difference, quantifiable difference between the various stages of this process. And that's new for the experimental sciences to be able to do that, to be able to have a numerical or this visual descriptor for each stage in this process. This is new. Before persistence, what you do is you have experts who've been staring at these pictures all their careers, and they can tell you the difference. They can't explain to you how they know this, because if you stare at tens of thousands of these pictures, they make sense to you, right? And that's how we learn. This is the image that's the pattern recognition that our brains do exceedingly well. Okay, and there are all kinds of wonderful systems. Skyrmions are quasi-particles which are toroidal, if you like. They are essentially toroidal singularities in electromagnetic field. And you can organize these toroidal singularities into these semi-organized systems. And they are fantastically cool. And again, applying the same strategy as before, we can distinguish, or we can quantify, if you like, the time evolution by computing persistence, calculating distances, and creating this heat map of the resulting metric space. So while these are oh, is this my phone? So while these pictures are of course evocative, being able to quantify the process is fantastic, and those metric spaces have 2 or 3 dimensional visualizations through all kinds of low dimensional embedding and so on. Okay, so this, I hope that's at least a little bit interesting to you. But now let's think about how to deal with disorder. Okay, so order typically in our mind connects with something like a lattice or a variant of a lattice and so on. So persistence, as you well know, this is actually true, very elementary. Persistence will give you geometric information about this. You see, when you calculate persistence of this very regular setup, there will be a class with a birth and a death coordinate, and those coordinates will directly correspond to the geometry of your system. I know you know it, but it's easy to forget when we think about this as a part of topology. It actually understands geometry as well. Okay, so an ordered system will typically create a very sharp persistent homology diagram. If you have something messy, as you well know, it will be far messier. There will be some kind of signal that indicates there may be some overall structure, but it will be messy. So this is where we come to this quantification of disorder. One more elementary point, and this is the final one, is that persistence is very good at distinguishing configurations. So you can play this game, well, have an arrangement of squares, like squares 1, squares 2, okay? And have an arrangement of triangles. Compute persistent homology, okay? It will look the homology will look slightly different for triangles and squares. And in fact, you can calculate the metric space of this very simple arrangement and embed it in the plane. And squares are here, triangles are there. You see? So this very simple-minded example shows what we know very well, that persistence is tremendously good at classifying these configurations, arrangements of things. Okay, so a disordered lattice will be a regular lattice distorted. Okay, so you take a regular lattice with a number of sites, and then just displays from the ideal order by using some noise, which is drawn from the uniform distribution, and this parameter S sub d is the strength, is the statistical measure of strength of the uncorrelated disorder. And we were motivated here by a very interesting paper by Florian Sterl and his co-workers that did all kinds of simulations. So these are synthetic distorted lattices, but the point was that you can then model the response in a physical experiment where light shines on something and you try to see the response of this disordered lattice. Okay, so the setup varied between something completely ordered, completely random, and something which is partially random. There are several ways in which you can make it less random, and that is, apart from the statistical disorder which is here, okay, it's the measure of how far these things will be moved away from their preferred perfect position. There is something called correlation length, and that's essentially that determines whether these dots know about their nearest neighbors or they don't. And if they know about their nearest neighbors, how many? Okay, how far this interaction would go. So in fact, in some sense, this correlation length attempts to integrate this disorder to impose this, if you like, distorted partial order in a completely different meaning of the word than what Tamal said in the lecture before. Okay, so this correlation weight, you can do it in any number of ways. That essentially says that the influence one particle will have on another will rapidly decay with the distance. In fact, it's exponentially fast. And the total disorder is something like this. So we created some disordered lattices, So this is, if you like, with no correlation length, with some correlation length and some other correlation length. Sorry, the same correlation length. But the point was, the point of these pictures is to show you that even if the statistical parameter and correlation length are the same, if you do it many times, each time you will get something which is slightly different. So you begin to think that those standard parameters to describe disorder are maybe not sharp enough to actually reveal what's interesting. And in fact, then you start thinking, okay, would persistent homology contain some additional information that would help? And indeed it does. In degree 0, there is what we already use, the structural heterogeneity. This is what we use to track time evolution. And that's just the total length of the persistent diagram. But then, using that, we can calculate something which would be like an entropy type expression, which attempts to quantify the amount of information contained in a particular arrangement. So that's supposed to mimic Gibbs type entropy. This is maximal, so it kind of works backwards to our intuition. It's maximal when this length, this characteristic length is constant, so for periodic lattices, and it measures the degree of order rather than disorder, but it's invariant with respect to scaling, and it's very useful for that. But to make sure that we measure disorder rather than order, there's a very simple modification of something we call the topological disorder, which is a very simple modification of persistent entropy. All right, so the hypothesis we set out to test is that if you have a system with low topological disorder, this should still have physical properties, good properties. Right, and we actually, right, so we demonstrated as follows. Of all the lattices, so we created many lattices with a given statistical disorder and correlation length. And then we selected from those lattices something with low topological disorder, intermediate topological disorder, and large topological disorder, and we modeled the response in a way that Sterl did. And I hope you see, blue is low topological disorder, orange is medium topological disorder, and green is high. So you see, this is quite remarkable. You have a family of randomly constructed layouts, and from this family, topological disorder will allow you to select ones which seem to be slightly more organized than others. Okay, statistics will not show you this, but topology does. And we went further. We actually built these things. So this is, if you like, closing the loop. So this is, we go from physics to topology. So we actually selected those configurations and we made them. Okay, so this is no longer simulated. This is an electron microscope picture of something that, when I say we built, it wasn't me. I have no idea how to do this. But I know people who can. And then we actually run an actual physical experiment. This is no longer simulation. This is an actual physical experiment. And we made setups with high and low topological disorder for various values of statistical disorder and the correlation length. And it agrees beautifully. So just for comparison, here is what an ordered lattice would do. the black line is what an ordered lattice would do. So this is like the best possible signal you can hope to get. But you see, every time where there is low topological disorder, it gets fairly close to this ideal signal, and every time there is high topological disorder, it's not so close. So this is quite remarkable. That I think this is a wonderful example where topology can actually inform the design of these things. And yeah, you may say, okay, this is not particularly sophisticated, but we have to start somewhere. So this I think is very good. Part of that, all right, I already mentioned that there are difficulties that you have to overcome in image processing and so on. So going towards the self-organizing systems, we looked at assemblies of nanocubes, so tiny, tiny cubes, and tried to figure out if there is any structure in them at all. And this turns out that this goes beyond the level of organization is so slight that this methodology struggles with it, but also at this size, it's very difficult to actually process these images so that you can see where the nanoparticles are actually located. If you do some sort of cleaning, you go from an image taken under an electron microscope to a cleaned image, but then you need to figure out which of these are actual nanoparticles and which of them are artifacts of the process. Okay? So to go from here to here, you can attempt to train a neural network to allow you to help you detect which of those are nanocubes. So this is, if you like, image processing, and this is some neural network that we built. And here's another example of where we get to the limits of what's applicable, and we have to start thinking about this again. And the point is that electron microscopes give you tremendously high magnification, but they can only see a small area. If you want to see a bigger area, you get a smaller magnification, and then persistence, calculating persistence is essentially not feasible. But even so, if you attempt to do some persistence with statistics, with 3 samples, you can just about make out some differences in that if you enhance those images using AI or neural networks, well, let's do it, then you can just about discern the differences between those various samples, which to the naked eye, they look messy. As when you look at the 3 of them, and they just look messy. And yet, there is still some difference between them, which is exemplified in these diagrams. This is, if you like, the clear distinction that the 3 curves that describe the response of those samples to light indicate. Okay, so this is all things that we did recently, but then Paavo and our collaborator Mark Burford, we started thinking about, okay, so there are some classification problems within neural networks, and can we actually understand how that works? So this is shifting towards the analysis and understanding of neural networks. So a typical classification problem, and this is the kind of thing that I talked about already, is that you have some data and you have some labels, and you want to construct a function from data to labels so that you can give a label to each element of data. All right? So this introduces the notion of decision boundaries for neural networks. And the decision boundary is what you think it will be. It's a subset of the space in which your data lives, so that when you're on the boundary, you will always find examples of points with opposite labels nearby. Okay? And, okay, so there was a picture here that is not showing. Okay, I'm sorry, I don't know what happened. Yeah, it's a failure of translation. So there was a picture here to describe how a typical neural network works. So here's a picture of a typical data point. What's that?
I think you steal it from background, they just cancelled it.
I see. So you did, yeah. It was from our paper.
Okay.
This was actually taken from our paper. So
everyone who read the little prints can
okay, but let's not dwell on this. So neural networks are trained to minimize a loss function, and a loss function typically means the distance between what label you expected to see and what the function, what the function you are constructing is showing to you. Okay, so if your data set is more complicated, then this training process will attempt to modify the decision boundaries to incorporate new data that may have been added to the point. But there is a problem with that. So this is some of the experiments we run with Pablo and Matt. If you have a data set that consists of those swirling spirals of orange and blue shapes, and you try to classify that, okay, after like 100 iterations of your training process, you get decision boundaries that look nothing like your set, right? So it's quite clear that this network, if you use that for classification, will be wrong most of the time. This is the thing that underpins, all image recognition and self-driving cars, and yeah. So you keep going with that, and the decision boundaries get more and more complicated, and after like 900 iterations, you have something that will produce reasonable answers some of the time, but there are still regions where things are just wrong. Okay? If you keep doing this, if you keep going with that, there is a danger of overfitting, which means your network will essentially memorize all the data that you showed it, and will memorize all the labels, but will not be able to do anything else. If you show it any other data points, it will flip. So for classification tasks, the efficiency, the performance of a deep neural network is determined by the structure of those boundaries. Okay, and the model will be efficient if its decision boundaries will fit the requirements of your problem. And okay, so the problem now arises: can we actually use topology or geometry and topology, so a combination of them, to say something about the structure of those decision boundaries, the shape, the size, whatever. However, these neural networks typically operate on very high dimensional data, and persistence doesn't work so well in high dimensions. And Yasuhiro Oka and his co-workers have a wonderful paper that discusses exactly that point. And persistence just doesn't work so well. And this is a very trivial manifestation of that phenomenon. If you want to calculate the persistent homology of a cylinder in some small dimensions, the signal should be that you have one thing, right? You have a cylinder, and it has essentially one loop. So one loop, one signal in degree 0, and one loop in degree 1. But then, as you take the same cylinder, so I'm keeping the dimension of the cylinder fixed, but I'm embedding it in a higher and higher dimensional space. There is always noise in sampling points. In sampling points from the cylinder, there is always noise involved. And if you like, in dimension 5, you clearly have this cloud of noisy points. You still see your signal. There is noise here, and there is still signal that you have one piece. But if you keep increasing the dimension, essentially the signal disappears into the noise. You no longer see what it is. Yes?
How many samples you have? So
So-
does the number of sample points increase with dimension?
Yeah. With dimension, yes, you have a bigger cloud, so yes, you increase the sample.
Exponentially, or
Sorry?
will you increase exponentially?
Yeah, that's an excellent question. I mean, the answer is, a simple estimate shows that if you want a similar density of estimates, you need to increase the points essentially exponentially, right? So imagine that you have a lattice into dimensions, like call it 100 by 100. You have 10,000 points. That's roughly the size of your sample, if you want to understand that you have a lattice. But if you increase the dimension, so you go from cube to cube, you will get like 100 points to power of your dimension. That's roughly how this is the sample space from where your noise will come. And yes, you need more points, but there is also more ways to get it wrong. All right? So you see, that's some of the point. So persistence will not help. Or if you want to use it, you need to modify it. So here's a very messy diagram drawn by Matt. So this was not taken from anyone. Matt did that. So. And so you have two data points, data sets, orange and blue, and you have some decision boundaries. We are interested in trying to estimate the size and shape of tubular neighborhoods of those decision boundaries. And calculating volumes in higher dimensions it's not trivial. You have all kinds of phenomena there, but the intuition says that the volume of that yellow tubular neighborhood should be smaller than the volume of that purple neighborhood, because that's how our intuition works. There are many phenomena in high dimensions that just work differently to how we think about things, and that's typically called the curse of dimensionality. For instance, if you take a randomly selected family of vectors, just take some gigantic dimensional space and select a family of random vectors. The probability that those vectors are pairwise almost orthogonal grows exponentially with the dimension. So essentially, if you like, a random selection of vectors in a high dimensional space will essentially always be orthogonal. All right? That doesn't happen in smaller dimensions. If you select a family of points randomly, they will typically have similar distances. The pairwise distances will be typically similar. Right? There is also the ironically called blessing of similarity, of dimensionality. In high dimensions, data is far less variable. You can actually test this. So if you take two standard test sets, MNIST and Cypher10, Cypher10 is much higher dimensional than MNIST, then a measure of distances for the high dimensional set. Clearly, the distances between data points are more uniform in the high dimensional set than in the lower dimensional set. Okay, but right, so what we did here, and this is almost the end of my talk, what we did here is we went back to classical formulae of files from the 1930s, so it's almost 100 years ago. I don't quote them here because they're just too complicated to reproduce in a simple slide. But Weil actually did think about how to calculate volumes in high dimensions. We created a methodology for estimating the volume of the decision boundary, and this involves actually using what you need to use is create adversarial attacks. An adversarial attack is an artificially inserted data point which is close to points with one label, but which forces the network to give it an opposite label. Okay, so that's what an adversarial attack is. So essentially, you select randomly points, you randomly select points reasonably close to the boundary, and then give each point some volume, some shape whose volume you know how to calculate, for instance, a cube, and then estimate how many points with each label you find in this in that cube, and putting this all together gives you some way of estimating the volume of this tubular neighborhood. In fact, we found 3 ways of doing it, and it all works. So it turns out that on the experiments that we run, volume is or seems to be a good estimator of the complexity of the decision boundary, and we run experiments on standard test sets, MNIST, fashion MNIST. So MNIST is the handwritten digits data set. MNIST is, the fashion MNIST is its analog, where you want to distinguish icons of items of clothing, and I've forgotten cipher 10. Okay, but
Those numbers of the buildings.
numbers of buildings. Yes, cipher 10. Yes.
Google Street View.
Yes, from Google Street View. Yes, Google Street View gives you photographs of building numbers. Thank you. And cipher 10 is a classification of that. And our hypothesis that network architectures which are well suited to the particular learning task will be the ones with smaller decision boundaries seems to be well confirmed in these experiments. So this is interesting. And we hope that the paper will be, a version of that is available already on arXiv, but final version should be ready soon. And it just remains me to thank the team, collaborators, physicist friends from Southampton, Małgosia Kaczmarek, Sasha Buchnev, mathematicians, Amaranta Membriel-Solis, Tatiana, who is now in Yerevan. We have a very nice group in Southampton: Tristan Madeleine, Gianpaolo D'Alessandro, Ruben Sanchez Garcia, Andrea, who's here, Ur Kantork, and then collaborators from further afield, people who gave us the Skirmion pictures, Haley and Ivan and Luciana and Francesca gave us the nanotube pictures, and Paolo and Matt, we collaborated on the decision boundaries, and we are grateful to the sponsors, and I'll stop here, so thank you.